So welcome everyone to Chemistry Lover, and today we have with us, this is my senior, Sarojit Das from ICHR Kolkata. So I personally know him. I can say he's a great teacher because he explains things very well, and you will see that in this lecture. And let me tell you that it is now 11 p.m. of night, and he did column for the whole day because he's doing work in organic chemistry lab, so you can think how much pressure he have. And as I requested him to do this lecture, so that's why he came after finishing his so much work. Okay, so it's not yet finished, right? So you can see at 11 p.m. he's coming to my room and he's making this lecture for you. So be passionate and be concentrated in this lecture. So this will be very helpful for you. So he doesn't need further introduction. So let's start with this topic.
Okay, hello everyone. This is your favorite channel, Chemistry Lover. The proprietor of this channel, you know, Muhammad Shahnaz, is my junior, and he told me to give this couple of lectures. So I decided, since he is teaching you the organic chemistry, let me be in organic, that is inorganic. So I have planned to discuss on electronic spectra of transition metal complex. So this is a very important topic, as you know. So without any further ado, let's get started. So first of all, as you can see that here is electron. So that actually means it is associated with some electronic transitions. And spectra. Spectra is a plural form of spectrum. So what is a spectrum? So spectrum is basically what you get while doing some spectroscopic measurements. Now, what is spectroscopy? So, first of all, these things should be very clear. Spectroscopy. So, spectroscopy is basically light, matter interaction. Matter you understand, but what is light? Light is an electromagnetic radiation. So if you have X, say X is here, you have Y-axis here, and you have Z-axis over here. So let's say that you have what you have? You have one electric field which is basically sinusoidal wave. So that is propagating along X and Y. Sorry, that is propagating along plus and minus X axis. So here you have this one, and here you have this one. So this is your electric field.
It is along Z axis.
No, this is along X axis. Plus X, minus X.
Okay.
And you have another one which is orthogonal to this X. That is your along plus minus Y axis. So that is your magnetic field. So your electric field vector and magnetic field vector are propagating like this, as a result of which you get the vector sum, which is your electromagnetic radiation. Now light is an electromagnetic radiation, so when it falls on matter, certain amount of it is getting absorbed by the matter and rest of the light is being transmitted or emitted, what you see. So basically you see the complementary color of the visible rays where it absorbs. So now let me introduce you some range basically. So that range will be, so whatever we are going to do, that is basically UV visible spectroscopy. So that is UV vis spectroscopy. So this is actually, you have here. So if let's say this is 200 nanometer and this is, let's say this is 1000 nanometer. Now let us divide into several segments. So this is your 400 nanometer. Okay, so this is another segment, 600 nanometer. This is another segment, 800 nanometer, and finally 1000. So this region, this 200 to 400, this is basically your UV region. And whatever you have this 400 to 800, roughly, why I am saying roughly, I am coming to that. So this is your visible range. This is also. So, why I told roughly? So, as you know, this is VGO, which is basically your this visible range. So VGO, V stands for violet, I stands for indigo, B stands for blue, G stands for green, Y stands for yellow, O stands for orange, R stands for red. Now what is UV? Ultraviolet. That means it will be remaining before violet. So this is your UV. And what is IR? It is infrared. That is after red. So you have IR, some over here. So what is this range? Basically this is your near IR range or NIR. So if you are doing some research, so you may have heard of this NIR region. So basically your violet, indigo, blue, green, yellow, orange, red, these are on this visible range, and it ranges from basically violet is your 400 nanometer and deep red is your 750 nanometer. So it is not exactly 800, that's why I told you. Okay, so now we will tell something about this. As you see, this violet, I already written how much value, 400 nanometer. Okay, then indigo range is very small, so let's discard that one for the time being. Let's write blue. So blue is your 450 nanometer around. Then you have blue green, that is your 490 nanometer. Then you have green. Don't worry, I am not remembering this. So I have some mnemonic for you, how you have to remember all these things. So green is going to be your maybe 530 nanometer. I will check once I complete the writing. So violet, blue, blue-green, green, yellow. Okay, so yellow is around, so you have violet, blue, blue-green, green, yellow, around your, let's say 580 nanometer. Okay, so orange, 620, and red 700 nanometer, and deep red I already mentioned. That is your 750 nanometer. Now let's check whether I have written it correctly. So violet is 400, blue is 450, blue green 490, green is 530, yellow is 580, orange is 620, red is 700, deep red is 750. So I have written it correctly. So you can remember this one, 400. Anything you have to remember. So violet is your 400. Now you add plus 50. So you will get this blue. Then you add plus 40. So you will get 490. Then you add another 40. You will get 530. You add plus 50. You will get 580. You add plus 40. You will get 620. You add plus 40 plus 40. You will get this 700, and this 700 to 750. You add plus 50. So this is how I remember. If you find it useful, you can remember, but it is not required to remember these things. It's not that much important. But what is important basically, so you have three basic colors out of it. Okay? So what are those three basic colors? Basic colors are red, green, and blue. So which are the basic colors? Your basic colors are red, green, and blue. So what happens if you basically, R stands for red, G stands for green, blue stands for B here, and if you have equal amount of R, G and B, then you will get white. Okay, so again, if you mix these two colors, so if you are mixing this blue and green, you will get in between, that is bluish green. It is often known as cyan color. Cyan. Okay, so if you are mixing green and red, you will get yellow. Okay, so if you are mixing these two, you will get yellow color. And if you are mixing red and blue, you will get purple color, nearly violet. Purple color, or it is often called magenta. So blue plus green, that will give you cyan. Green plus red, that will give you yellow. and red plus blue, that will give you magenta or purple. So this is one important aspect that you need to know. These are three basic colors and their combination. So I hope you have noted it down if required. So I am rubbing it off. So next the thing is that so what we do in UV visible spectroscopy, so we make a solution of a sample, so that is often being made in your suitable solvent, let's say DCM, so or dichloromether. So you have a cuvette over here, this is called cuvette or cell, where you need to fill up with your analyte. So your analyte in a suitable solvent. Now what you do basically, you place it in UV visible spectrophotometer, and there is a lamp. So this lamp will give you intensity of light, let's say I0, as a function of lambda, that will incident on this, and some of it will be absorbed by the solution and rest of the thing will be transmitted. That is also as a function of lambda, and you record it. So when you record it, this is very important. So when you record it, you basically plot. Here you have this OD or optical density, or it sometimes is written as absorbance. I will define it shortly. So this is basically your absorbance. Okay, so this is your y-axis, and here you have lambda or wavelength. Okay, so OD is a function of lambda. So y here is x. So y is a function of, you plot basically y is a function of x. So what is y? Y is your OD or absorbance, and absorbance is defined as logarithm of I0 by x.
Yes, not visible if you just.
Which one?
Actually, when you are writing like this, you are barrier to this.
Oh, I am the first.
Yeah.
Do this. Okay, I hope the viewers won't mind.
Yeah.
Viewers will forgive. They are very much generous, I guess. Okay, so this is basically your absorbance or OD. So you take this ratio I0 to I and take the logarithmic expression of that one, that is your OD. And since it's a ratio of the same thing, so this is actually your unit length. Now some of the paper you will see that they write OD and within parenthesis A dot U, and this is arbitrary unit, not atomic unit. Many people get confused over here. This is arbitrary unit, not atomic unit. Okay, please do remember. Now another important thing, when you scan, when you provide this, when you scan basically, so this wavelength, so you start scanning from the higher wavelength. So never ever think that I am taking the spectrum within 200 to 400. That doesn't mean that it starts taking the spectrum, starts recording the spectrum from 200 and then goes up to 400. It never happens like that. So it happens in the reverse fashion. So it will start from the 400. So your spectra basically you will get like this. Let's say some over here you have found. Okay, so your spectra will look like this. So it will start from the higher wavelength and then it will come to the lower wavelength. These basic things you need to understand. Now this is actually incident light and this is actually transmitted light or emitted light. So what is being absorbed basically? I0 as a function of lambda minus I as a function of lambda. This much is absorbed. Okay. So these are the very few basic things. Now we will gradually proceed further. Okay. So have you ever wondered why different ligands give rise to different color? So if I tell you this hexa aqua nickel 2 is 2 plus versus hexaamine nickel 2. So the first one is your green color, whereas in the second one is blue in color. So that essentially means that it is the ligands which dictating the color of the complex, because in both the cases you have same metal ion in same oxidation state. So what is playing the role is your ligand molecules. Now in case of transition metals complexes, as you know, what is transition metal? Transition metals are those who will possess either unfilled or partially filled d orbital at their stable oxidation state, any stable oxidation state. So in that perspective, your that zinc, cadmium, mercury, these are not transition elements. Many people get confused with zinc, cadmium, mercury and they consider them as also the transition metals, but they are not, because they don't have unfilled or partially filled d orbital in their any stable oxidation state. So let's come to the point. So this is basically the ligand which dictate the color of the complex. So that's why it is called ligand field spectra. So when you see the ligand field spectra, it should be kept in your mind. It is basically the metal d orbitals are getting some sort of arrangement is there when the ligand approaches to a naked metal ion. That I am assuming that you know the very basics of this coordination chemistry, and I am not going into details. So considering that you have filled up the prerequisite of this course, so let me tell you further. So what happens basically, so you have several d orbitals that will get aligned in a particular at a particular energy state when you when different ligands are approaching to this metal ion. Now what happens basically, so there will be different extent or different ways of transition between these differentially stabilized d orbitals, and that will give rise to the spectrum. Okay, so now let me tell you a very popular textbook example, which is your titanium H2O 46 3 plus. Okay, so titanium H2O 46 3 plus, hexa aqua titanium 3. Now the thing is that it is basically D1 system. Okay, and if you record its UV visible spectrum. So you will see one harm. So when you are drawing, I hope you will draw from this side, not from the reverse. So somewhere you will see the absorption around this 500 nanometer. Maybe, if I remember correctly, it's 5%. Okay, so 500 nanometer. Now, that essentially means you have one harm. That means, so there is only one transition that corresponds to this one. So this is not structured. This is not structured. That only means there are two energy levels. Maybe your ground state energy levels and excited energy levels. Now this electron is here. Let's say this electron is going here. So I am not making it paired. I am just, for the sake of understanding, I am telling you. So this is just lifting up. Okay. So now the thing is that there are several vibrational levels. So if you actually plot, you can plot like this and you can show the transition like this. But for the sake of clarity, I am just telling you that you are, so this is basically an electronic transition, right? So electronic transition means electron will transit from ground state to excited state, first excited state, and that is giving rise to the spectra. So if there are more transitions, then you will have structured band. So you will get, instead of getting a broad spectrum as we got here, you will get some fine structure, maybe looking like this. So there will be several ups and downs and it will be structured. Okay, so these things should be clear. Now one very important thing, I will slowly come into that. So previously I thought that I will give this entire lecture one, but it could be boring, and as I am the first time I am preparing this time facing the camera, so Sarnaj is smiling behind the camera, so it is always very difficult. So when he makes the video, there is no disturbing factor, but I consider him as a disturbing factor now. So
I'm not disturbing at all.
He is not disturbing at all. He is very enthusiastic guy, as you all know, and
I'm not that much enthusiastic.
okay, so he is very generous. He's smiling. So let's come to the point. So I thought to bifurcate this lecture into two parts. Part A, we will talk in this video, and slowly I will inculcate the habit of facing the camera, and by the time you will get the next video.
So after that, he may give you more lectures. If he just accompanied with the video making, he will give you more lectures. He will be benefited, right? So this is good for you.
Okay, so I don't know whether it will be good for you or boring for you, but I feel that it will not harm you. That's the most important thing. Okay. So one very important thing we will now talk about, that is the ground state term symbol. I hope that you all have heard of it quite a long time. Many times you have heard of it. So ground state term symbol. Okay. So ground state term symbol, we will consider only Dn ions over here. Okay. So Dn ions where n belongs to any integer. Okay, that means n could be 0, 1, 2. Let's say positivity. Okay. So you have this D0, D1, D2. Okay, D0 means nothing, so spectra will not be there. So it's D1, let's say. So D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. So I will show you to calculate or to get this ground state term symbol. Many of you already know this, but it would be a recapitulation for you. So let's get started. So I will show you for D1, D5 and say D9. That's fine. So rest of the things you can do yourself and check with the textbook if you have done it correctly or not, or you can put it into comment section as well. So the thing is that, so let's get started. So D1. So D1, how do we compute it? So d orbital, you know, there are 5 d orbitals. I missed one room. So here is another room. So you have D1 over here. So you have plus 2 plus 1, 0, minus 1, minus 2. So these are actually your ml. Okay. So your capital L will be summation of small ml. So that will give rise you this 2. There is only one. So just a recapitulation. When L is 0, you will have S. 1 is P. Okay. 2 is B. And 3 is F. So you know the full form of this SPDA? Shahnaz knows? He also doesn't know. So S stands for sharp, P stands for principal.
I heard about it at some time, but
D for diffuse and F for fundamental. So I hope that Shahnaz has read it. He is a die-hard fan of organic chemistry, and no organic chemistry can avoid Peter size. So it is written in Peter size. Sharp, principal, diffuse and fundamental. Oh, by the way, this is your which quantum number? ML?
ML is
azimuthal quantum number, right? So
actually by reading Clayton, I forgot Peter size.
Yeah. So he is reading Clayton for you only. So you are responsible that he could
not for them, for me.
So yeah. So let's come to the point. So you are summing up these azimuthal quantum numbers to get this L1. So L is your L is basically your orbital angular momentum. So you will also have spin angular momentum. Okay. So spin angular momentum is basically your how many unpaired electron is there? 1. So basically your S is equals to 1 by 2. So that is your spin angular momentum. So when they couple, basically you get LS coupling, which we call often, there is a name. This is Russell-Saunders coupling, RS coupling scheme. Yeah, right. So this is another your spin angular momentum. So he was telling about this RS coupling. Let me ask him something on RS coupling.
I am not here to answer anything.
Okay. You are enjoying that I am in deep trouble. Huh? So basically, this Russell-Saunders coupling is valid for low molecular weight atoms. Yeah. So it is valid up to say chlorine, but it is basically fairly good enough, like we can say, for early transition elements, maybe your first row transition elements. RS coupling is valid. So deviations come as you go to the heavier containers. So these two momentum, orbital angular momentum and spin angular momentum, they can couple and they actually give rise to a new quantum number J. That is your spin orbit coupling. So this quantum number is associated with spin orbit coupling. So spin orbit coupling. So basically when you, okay, so I told you that L, when 0, it is S, capital L I am talking about. 1 is P, 2 is D. So term has come D. Okay. So what would be the term symbol now? term symbol basically is your 2s plus 1 Lj. Okay, so 2s plus 1. Now what is j? J is basically your L plus s to L minus s. So it ranges from via 0. So L plus s to L minus s via 0. There is 0. Dot, dot, dot. Okay, so when you take L minus s and when you take L plus s. So if you have half field or lower than half field, then you have lower value of j. You have to go for lower value of j. Half field, I repeat, half field or less than half field. That means D5 or D4, D3, D2, D1. Or if you have more than half field, that means D6, D7, D8, D9, D10, then you have to go for higher value of j. That is L plus s will be from D6 to D10 and L minus s will be for D1 to D5. Is it clear? Okay. I hope it's clear. So what would be the term symbol for this one? So 2s plus 1, that is actually give you 2 into 1 by 2 plus 1, that is 1 plus 1, that is 2. So you will have this, let me write over here. So you will have 2s plus 1, that is coming as 2. If you put this value as half, L is your D and J will be your L plus S. So 2 plus half.
Not L plus S, L minus S.
No, there are two values. Huh? J will be either your 3 by 2 or, so basically L plus is how much coming? 2 plus half. So that is your 5 by 2. And L minus S is your 2 minus half. That is your 3 by 2. So what I told that if you have half field or lower than half field, you have to take the lowest value. So that is your 3 by 2. So similarly you can do it for D5 and D9. I thought to get it done, but you can do it yourself. I hope it's clear now what you need to do. So once you do it, I will tell you the mnemonic of this D1 to D10, how you will remember this ground state term symbol. So I think let's stop here. So wish you best of luck, and thank you Shahnaz for giving me this opportunity. I am trying. I am a learner, so I am learning how to face the camera. So it is new for me, so I am enjoying, and I am thankful to Shahnaz for giving me this opportunity once again. So I hope you have liked it. So if you are new to this channel, this chemistry lover, so Shahnaz is a very enthusiastic guy. He is doing great. I am very much impressed and happy. So please subscribe the channel and don't forget to press the bell icon.